Welcome to easyedu. Today, we'll derive one of the most important results from Bohr's model of the atom, the Bohr radius. This is the fundamental size of an electron's orbit in a hydrogen atom. Let's dive into this fascinating topic. In 1913, Niels Bohr proposed a model for the atom to explain the stability of electrons and the discrete spectral lines of hydrogen. Bohr's model is based on two key assumptions. Electrons revolve around the nucleus in circular orbits due to the Coulomb force between the positively charged nucleus and the negatively charged electron. The angular momentum of the electron is quantized, meaning it can only take discrete values. First, let's analyze the forces acting on the electron. The centripetal force that keeps the electron in its circular orbit is provided by the Coulomb force between the electron and the nucleus. Here, K is the Coulomb constant, E is the charge of the electron, R is the radius of the orbit, M is the mass of the electron, and V is the orbital velocity. Next, Bohr's second postulate states that the angular momentum of the electron is quantized and given by the equation. Here, n is the principal quantum number, which can take integer values like 1, 2, 3, and so on, and h is the reduced Planck's constant. We can now relate these equations. From the angular momentum quantization condition, we can express the velocity as. Substituting this velocity into the centripetal force equation, we get. Simplifying, rearranging, and solving for radius, we will get. This is the general formula for the radius of an electron's orbit in a hydrogen atom. Notice that the radius depends on, which means higher orbits are farther from the nucleus. For the ground state n is equal to 1, the radius is called the Bohr radius. Substituting the known values for constants, we get. This is approximately a fundamental constant that represents the size of the hydrogen atom's smallest orbit.